Good morning, everyone. Welcome to day 2 of week 2. We had a lot of great sessions yesterday on LLMs, both on the individual, like the fundamentals by Nora, who gave us a great overview over NLP and how we got to transformers, and then Razvan talking about like a little bit of the theory of what like the theoretical limitations are of current LLMs. And today it's really amazing to have Rao joining us. He is a professor of computer science at Arizona State University. He's a fellow of the Association for the Advancement of AI. And he does a lot of work on planning and decision making, and I think recently a lot on reasoning with LLMs. And he's gonna talk about that both this morning and tomorrow morning. So please welcome Rob.
Thank you, guys. Can you hear me, Fabian?
Yeah.
Yeah, you can hear me fine, right? Okay, good, thanks. So folks, the slides are available actually in case you want to follow. That's for today's lecture. I will, post the ones for tomorrow. I had actually made a Discord channel, but since you already have the Slack, you can please, I understand that I'm doing it on Zoom, and so it's not as easy to stop me and ask questions. I actually have a separate computer with just you guys that on my side. Right now, I can see you guys. And so if there is actually anybody trying to ask a question, I'll probably try to see it. But even otherwise, please post questions between today and tomorrow and even after tomorrow. And I would be happy to answer them. And also, if there's any questions or links or something that you're looking for, I would be happy to answer them. Okay, so that's basically the thing. As I said, the slides, I already posted it on the Slack too. So in case you want, you can take it from there. Okay, so let's get started. So let's see if this thing is working. One second. Yeah. Yeah, okay. So first, let me start by actually saying that I did give a talk in machine learning summer school back in 2006. It's in Canberra, and that's me giving that I think lectures on learning techniques for planning. And then that's Doug Aberdeen down there in his shorts, actually introducing me, and I'm onto the side. Anyway, and I had a lot of fun at that time. So when a zillion years later, when Fabian asked me to come and talk in Melbourne, I was really excited to come actually in person. I have been to Melbourne and multiple times, and it's a lovely city. And there is no such thing as getting sick and tired of Melbourne. I would have loved to be there, actually hanging around in front of you guys and talking. It's always more fun to give lectures in front of people. But unfortunately, I had some, various personal constraints. So I am doing the next best thing. And I hope that you will still get something out of this, basically. So that's the story of why I'm doing this on Zoom. And as I said, actually, I set up a Discord channel, but either you can post there or you can actually post on the Slack too if you have any questions. And the slides are available there. Okay, and I also want to say that, as you saw, this is basically, the talk is about planning and reasoning capabilities of LLMs today. The basic idea would be that I would start with, as in a minute, I'll talk about the fact that I'm actually a planning person. In fact, that's what I was doing in 2006. I was talking about learning methods in planning. So basically, I'm going to look at the planning and reasoning capabilities of large language models. And the way I would do it is, like today, I would get you from, depending on the time, I would get you from standard LLMs, standard autoregressive LLMs, and just about also get into the reasoning models, which have the post-training phase and so have a slightly different characteristics about their ability to do well on planning and reasoning problems. And I would talk about how they actually achieve that stuff. And then depending on where we end here, tomorrow I would actually go even more into reasoning models and post-training, and also look at things like what do the post-training traces tell us about the quote-unquote reasoning and thinking of the LLMs, large language models. And I want to start, I haven't been there. So one of the sad parts of not being present along with you for the rest of the summer school is I don't quite know what other people have been doing. And I don't know how much, how much of the discussion on LLMs, etc., has happened. This particular thing, I want to mention that you might see that the parts of this talk are quite skeptical. Skeptical in the sense, not in a negative way. Science is about skepticism, about claims about reasoning capabilities, and taking it more seriously than just saying that I did a couple of empirical studies and it seemed to work. So I wanted to start by saying that, sometimes, at least in some kinds of crowds, saying anything slightly skeptical about LLMs is like this really mean guy, yelling at this cute puppy, which makes people mad at you very easily. So I want to tell you that I'm not talking about LLMs not being a great technology. They're amazing technology, but we want to understand what their strengths as well as limitations are. And in general, my quote is that, alchemy, the problem with alchemy is not that chemistry is a bad idea. It is that some people thought that essentially, if chemistry will act like nuclear physics if only you prompt it in a certain way. And that is the kind of thing that we want to push back on. As to what actually LLMs can and cannot do is something that I want to understand with respect to planning. So that's just to put in perspective. And again, I think that generally being skeptical about any claims is a good soft inductive bias for good science. And I hope that since you're all grad students and are early researchers, I hope that that part you will be agreeing with. So as I said, I'm in planning, and planning, of course, is about given a variety of the environments and their characteristics. The pink robot is actually trying to decide what action should it do next. That's basically the idea. And planning, of course, is figuring out the course of actions before actually doing it. For whatever it's worth, that pink robot was also there in the 2006 lecture. So, I think that thing has been made, I think, back in 1997 or something. So that's my talisman to some extent. And, I've done bunches of work in, how to generate plans in under variety of constraints of the domain dynamics, in stochastic and metric and temporal planning domains, and whether you have full models or approximate models or shallow models, and what sorts of different kinds of optimality techniques you might be actually looking at. These are all the things that I have done. So the question then is, so what I'm going to be looking at now is, to what extent are LLMs good at doing planning? That's basically what we're going to look at. Now, obviously, by now, and of course, even before you came to this, you already know you have various abstractions of LLMs. So my favorite abstraction is LLMs can be seen as essentially n-gram models on steroids. And basically, we think we have reasonable intuitions about n-gram models, but our intuitions fail when n is more than 2 or 3. We have ideas of unigram, bigram, and trigram models. But essentially, even the good old ChatGPT, the original one, is a 3001 gram model. And so the idea as to how, when it is trained on massive corpora, how it behaves is something that people didn't quite have good expectations. And so essentially, we realize that obviously I also assume that that basically we are doing these things the standard LLMs, at least, we are training them in the autoregressive fashion. We'll get to the post-training part in a minute. I actually would like to think of standard LLMs as actually taking all declarative knowledge that we wrote in natural language onto the web, and they're essentially trained on them as if, given this number of tokens, predict the next token. So I have my, some favorite example of mine. I'm in Arizona State University. Our rivals are University of Arizona, and so wildcats are essentially their mascot, and Sun Devils are our mascot. And so I made up this, sentence. So you clearly can see, and I don't think I have to walk you through this, that essentially you are, the system is essentially trying to train itself, looking at n words and predicting the n+1th token, and then taking the difference between its prediction and the actual thing that the sentence is saying. For example, if it predicted geese after wild, but the correct thing according to the sentence is cats, then you need to take the difference cats minus geese, and then throw that difference back propagate it through the large network that you have. And so basically in doing so, you obviously have an embedding space, and the embedding space, cats and geese are essentially some high dimensional vectors, and you're taking their difference, and that's how you're taking subtraction of the linguistic tokens. One thing I do want you to keep in mind is actually will be useful later on too, is that ultimately for LLMs, even though you and I see linguistic tokens, for LLMs, really what they are looking at when they're looking at a token is these high dimensional vectors. And these embedding spaces essentially are dense spaces. So some points in this dense space correspond to actual linguistic tokens. Infinitely many other points don't correspond to any single linguistic token. But then using a sort of a linear algebra views, you can say that there must be some kind of a if you think of linguistic tokens as a spanning vectors, then the ones that don't have a single linguistic token corresponding to them are probably some sort of a superposition, some convex combination of linear combination of the other tokens. So that's a useful thing to keep in mind. But for now, we'll just go back to just thinking of them in terms of linguistic tokens. And then the other part about LLMs that would be useful, I guess, for us is I think many of you probably realize it, but if you don't, that even for 3001 gram model with a 50,000 vocabulary, we are looking at a whopping 50,000 power 3,000 conditional distributions, because what an LLM is learning is a conditional distribution of the next token over the vocabulary. If there are 50,000 words, then it's basically figuring out, what are the probabilities for each of those tokens, conditioned on the tokens and n tokens that you have seen until now. And if the n is 3,000, then you essentially are talking about 50,000 per 3,000 conditional distributions. That's just way too many distributions. More importantly, if you start doing it in terms of the way normal bigram, trigram models are done by hand, most of them would be degenerate. There'll only be the probability that the same exact word will occur more than once after a 3,000 word context is basically zero. And so what you actually have to do is what's happening in these transformer networks is you are finding an approximation of these conditional distribution tables, and these compression functions essentially wind up giving non-zeros when they're zeros, and then less than ones when there are ones. And any compression kind of corresponds to some sort of a generalization. The interesting thing has been what sort of generalization have these LLMs been able to do, and you all know that they're pretty impressive, that they actually seem to be doing very interesting completions of prompts that we can give. And then couple of other things before we go off into the planning part is, obviously you can distinguish between retrieval in databases, retrieval in IR systems, and what you can think of as LLMs. Database retrieval, of course, is exact. You give a query, it exactly brings out the record that corresponds to that query. Retrieval in IR system, you give an approximate query, and then it looks for the actual real documents that are present in the library that are similar to this approximate query. In both cases, they're only giving data that's actually present in either the database or the IR corpus. In the case of approximate retrieval, what we are doing essentially is, in some sense, we are generating, given the query, we're generating the completion with respect to the LLM. And when you're doing that, this completion is not at all guaranteed to be one of the stored records. There is actually no stored records. And in fact, you also know that memorization occurs, more by accident than by design in LLMs, because they're essentially n-gram models. And so that's worthwhile keeping in mind. And so from that perspective, actually, I would actually argue that thinking of hallucination as more of a feature rather than a bug is actually a useful thing, because n-gram models are always hallucinating the completion for the prompt that you have given. Sometimes that completion corresponds to what you are hoping for, and in which case you give, basically sometimes the hallucination corresponds to your reality, but otherwise they're always essentially generating conditional distribution of, what is the most likely what's the most likely completion given this particular, prompt and the training data that's been given. So it's kind of worthwhile to keep that in mind, that hallucination is more a normal thing than just something that you can completely remove. Ever since 2022, 23, when GPT-3 came along, there were like regular things that hallucination will be removed, but that it's not a possible thing to do theoretically. One other thing that's kind of useful, again, in a more general sense about LLMs, is to distinguish between the style versus content and form versus factuality. LLMs capture the distribution of the data they are trained on. That's what any generative learning system does. Style is a distributional property. So LLMs are actually very good at learning this. And correctness and factuality tends to be, in many cases, instance level property. LLMs cannot guarantee it. To the extent correctness of a plan, for example, is important, that whether a plan looks like a plan is very different from whether a plan is correct, in the sense, can you execute it in the real world or in the world where that plan is supposed to be executed. And so it turns out, as I'm sort of hinting, when we look into the actual correctness of the LLM, standard LLMs, the plans that standard LLMs generate, they tend to be wrong most of the time, at least when we started, in 23, 24, and even until 24 September, for example, when O1 came along. But we'll talk about that in a minute. So one thing to keep in mind is that civilizationally, we had always thought that style is harder than content, that getting the right way of speaking like a real Aussie is much harder than just saying what the Aussie is saying in your own English, and so we tend to think that since style is harder for us and LLMs are so good at style, maybe they're also good at correctness, and that is something that tends to be not necessarily true. One last thing before we go into the planning part is, it's important to understand that ultimately LLMs are very much dependent on the training data, and this is basically, the training data is everything that anybody has ever written on the web. We haven't even come to the synthetic data issues, synthetic, like the post-training part. So if you just think in terms of even the memory effect, basically, it's sort of what they're trying to do is their LLMs tend to be critically dependent on the training data, and the training data is sort of essentially spanning the entire written record that humans bothered to put on the web. And so, but we don't quite know where it has holes and where it is complete. And so that sort of explains to some extent what has been called the jagged intelligence of LLMs, where depending on their training, they can at once be at the genius level, such as math Olympiads, but can also be maddeningly bad on simple common sense things. So I'm pretty sure many of you have seen this example that somebody posted when GPT-5 came along, that they asked GPT-5, Amazon sent me a left shoe instead of a right shoe and a right shoe instead of a left one. What do I do? And GPT-5 basically gives a long plan saying that was unnecessary and a very unfair thing that was done to you. Let's put them both, the shoes back into the box, and then write a letter and send it back to Amazon. That doesn't square well with the fact that the same system can supposedly do well, better than most of us in math Olympiads. So this is something that you just have to realize that it happens when you have a memory-based systems, because they will tend to have jagged intelligence. There are parts which they've been better trained on, there are parts they have not been trained on, and it's a useful thing to keep in mind. Anyway, so that's about just LLM's background. Most of you probably already have it, but I just wanted to give you my perspective. Like I said, the slides are there. So then the question, of course, is, can standard autoregressive LLMs plan? This is like, we started looking at it from like 2022 onwards when GPT-3 came along, then GPT 3.5 and 4, etc. So I want to kind of walk you through this, because even now people are actually making claims about standard LLMs without post-training anyway. So it's worthwhile understanding, can they plan? By the time we got into this in 2022 fall, there are already lots of these papers basically saying, indeed, actually they can plan. And in fact, what they did was they gave a bunch of prompts to the LLM, and it seemed to have given plans that seemed to be correct. And so they assumed that the prompt completion corresponds to the plan, so the planning abilities exist. We were little surprised at this, because first of all, there's like let's distinguish between acting versus planning. Acting, typically from the perspective of LLMs, is essentially kind of making function calls through API calls to outside services. And actually, LLMs are pretty good at figuring out API calls and making interesting calls. The planning part is, before you start the actions, do you know that if you do those actions in that way, you will actually get to the desirable outcomes or desirable states? And in general, what we will basically see is that LLMs cannot actually don't have good enough guarantees about the plans that they generate. In fact, they can be very bad in certain cases. But doing action is a very different thing. In fact, I give this example to my students that if you leave, I'm from a country which is quite different from the country you are sitting in, where this thing makes a lot more sense. If you have a gun lying around in your living room and you have a toddler, the toddler would know how to act with the gun, but they don't necessarily have a good planning ability yet. And so that would be a bad thing for everybody concerned. So in general, when agentic systems are concerned, if LLMs actually whether LLMs are able to start actions is less important, is not the only important thing. You want to also know whether there's any kind of a safety guarantee that the course of actions that they're planning to call would actually lead to desirable solutions. Now, the reason I was skeptical as to why, in fact, LLMs cannot, about the claims about LLMs doing planning when we started, is that, if you think of system 1, system 2 analogy, system 1, of course, is a reflexive knowledge, and then system 2 is a deliberative thing. This is obviously Kahneman's, metaphor about human brain, only a metaphor. And so if you, from that metaphor, I always considered, and I think I still consider even today, LLMs as a huge, giant system 1 for the entire humanity. We all have our own system 1s, but LLM is an extra system 1 for the entire humanity already. And so the question, of course, is planning and reasoning typically tends to be sort of a deliberative, in some cases, at least, it will require deliberation. Of course, if you have solved the planning problem once, or if you have seen the solution once, then you can compile it into a system 1 scenario. But most of the time, there would be cases when there will actually not be at the system 1 level. And so you would think that it should be failing if it hasn't actually seen these kinds of problems. Again, I'm talking about standard LLMs right now. So back in 2022, we started work, which actually got published in NeurIPS as a spotlight paper in 2023. That's on the planning abilities of large language models, a critical investigation, where we did this sort of, even though it was like, to me, it wasn't looking like it's even worth doing, because I thought those LLMs probably will make incorrect plans. I thought, okay, the only way to do it is to actually systematically evaluate, the LLMs on various planning domains. Now, obviously, I'm coming from, automated planning community, where we actually have a bunch of toy domains that we have used in a variety of what's called the international planning competition. If you ever took intro to AI, you would have heard of things like blocks world, which is like, there's a bunch of blocks in a particular configuration. You want to put them in a different configuration. And the plan would be, picking up blocks, stacking them on top of each other, etc. In logistics, there's a bunch of things in different cities, and you need to send them to different other cities with conveyances like planes, trucks, etc. And there's a bunch of other ones. In fact, things like Sokoban, which I forgot to put here. Sokoban is this very nice example where you are trying to push boxes into a configuration. And in fact, Sokoban has this, this property that actions are not reversible, because if you understand, when you are pushing the boxes, it turns out these are boxes that don't have handles. You can only push them. You can't pull them out. Once they are in the wrong configuration, you can't pull them out if they are actually flush with the wall. And so Sokoban is actually one of these kinds of domains. And those kinds of domains, the technical term in planning community and in general in AI is non-ergodic. That basically means you can get into a state from which you cannot get out during the execution. There are no actions to get out of those states. And if you have non-ergodic domains, that's exactly when planning becomes important, because you need to think about what to do before doing it. Because once you actually fall into your ditch or push yourself into a corner, you can't come out. Anyway, so we used both blocks world, logistics, and also Sokoban sorts of domains. I forgot to put that slide, maybe tomorrow I'll put it. But basically, all these domains, we checked them by kind of, prompting the LLMs. We considered a variety of prompting strategies. You can look it up the paper. We can do prompting in the PDDL format. PDDL happens to be a particular format that automated planning systems like this use to describe actions with their preconditions and effects. And the initial state is a set of propositions with their values. And the goal state requires certain propositions to be true and certain others to be false. And this is the planning situation. And so we could either ask the problem for the LLM in like the PDL fashion, or you can do it in a natural language fashion. So basically write the prompt in a sort of more Englishy fashion. We tried all of the different kinds of prompting strategies, and you can look at the longer paper, but the general sense is that basically, actually I'm only showing one set of examples there. The blocks world row in the table on the right hand side basically shows that, first of all, the numbers are not 100%, and they seem to be improving even as we were doing it. That particular thing was ended at 8:27:24. After that, I will talk about the reasoning models later on. But you'll notice that they were kind of improving, but they were still like below 57% even for part 3.5. And in general, GPT-3 in particular, which doesn't even appear here, that appears in the paper, was even less. It's like 20% or something, just for blocks world. Keep that in mind. Now, when the LLMs were improving, when the new LLMs came and they were solving the problems, one tricky issue about reasoning problems that you have to ask yourself, with LLMs, it's always an issue, is how much of it is because potentially of the contamination between the test data and the training data. And contamination is a feature rather than a bug with LLMs, because pretty much the entire world is essentially their data. And so, it is possible that more training data of certain kinds got available. And so that is a possible thing that we have to consider. So we had to ask, are LLMs, when, even as the blocks world thing, for example, when they're improving performance over different generations of LLMs, technologies, standard LLMs, are they kind of retrieving still in terms of because they have more training data, or are they actually kind of able to solve the problem from first principles? And the first principle solving would be needed if you have never seen this domain like before, like ever, right? And so the question, of course, is how do we make sure something like blocks world or even Sokoban, there's enough data about it in some form or other on the big wide web that you can't assume that it's not actually, LLMs have never seen it. right? So the only way you can do this essentially is to come up with things that you believe would actually be not seen with a very high chance. Even as we speak, actually yesterday, there was a New York Times article saying a bunch of mathematicians came up with proofs that they did in their working life in the last week or so that they didn't want to tell LLMs. They didn't put any notes anywhere on the web about these proofs. And they just basically encrypted them, and they want to see if LLMs can find them. That's the kind of thing you have to do when you're distinguishing between reasoning from memory versus reasoning from first principles. So if you see that, what we did was actually, an idea that's reasonably popular in planning community. This guy, Drew McDermott, is a very well-known researcher in planning. He's passed away a couple of years back, but he's actually basically came up with this idea to stop people from writing domain-specific planners back in early 2000, late 90s, saying take something like Block's World, change the object names and the predicate names such that you read this, it doesn't look like Block's World. So for example, instead of picking up a block, you'll say attack an object. If instead of unstacking a block from the top of another block, you say feast object from another object. And this kind of an obfuscation, you can do it either with English words with different meanings, or you can also do it with random strings. We did both random obfuscation as well as English word obfuscation. We did both of them. And we called these typically mystery blocks world and mystery random blocks world, or random mystery blocks world. And when we do this, you notice that the second row, the mystery blocks world part, actually everybody sucked. Right? All the Claude 3.5, Claude 3, GPT-4o, GPT-4, GPT-4 Turbo, all of them basically were about 2 of 500, 5 of 600 level correctness of these plans. Now, this sort of seems to suggest that maybe really what's going on to some extent can be that Block's World stuff is very much on the web, and this other thing that we made up doesn't exist. And so they had to actually solve. And by the way, to put this in perspective, if you took mystery blocks world and gave it to any classical planner, it will solve them correctly with the same ease as it solves blocks world problems. There is no difference. Changing the name, those of you who have any background in logic understand that changing the predicate names doesn't change the meaning. What changes the meaning is the connections between the predicates. If you keep the connections the same and change the predicate names, it's the same dynamical system. And so in fact, the problems can be solved with exactly the same speed and accuracy, 100% accuracy by classical planners, and yet these LLMs are just dying, right? So that sort of makes you realize that maybe indeed they're not actually solving the problem. They are sort of putting it together, not exactly looking for the solution for this problem, but putting together bits and pieces that seem to kind of, and when you put together bits and pieces, the chance that the concatenated-ish plan would be correct depends on certain properties of the domain that we'll be talking about in a minute. So that might be what is happening. One other thing, those of you, oftentimes when I do this, people basically do feel sympathetic to LLMs. In fact, one of the funny things about LLMs is that people think that it's okay that LLMs are actually solving Math Olympiad problems, even though most of the people can't solve Math Olympiad problems. But if they fail at something, they will ask, maybe lots and lots of people also can't solve it. It's unfair to LLMs, which is a reasonable question. So all I wanted to say is we did actually, it is indeed the case that mystery blocks world is a little more painful for humans than blocks world. Because we also tend to solve problems with both memory and reasoning. The point, of course, is if we incentivize people saying if you have a correct solution, you get money. If not, you won't get money. They actually take time and solve the problems correctly. We have done some experiments and reported that essentially human planners will take more time, but will get the plan correct. That's because they have both system 1 and system 2. On the other hand, we tried to offer money to LLMs at that time, and they didn't seem to take anything. So just like giving candy to them, it's not particularly useful. My point being that they're essentially sort of system 1 systems. And so they couldn't, basically couldn't do anything by you can't just give them incentives saying you'll give you money if you think more. Okay. Now, many of you also know that after this kind of a prompting, there's this other idea of chain of thought prompting. So basically, why just give a planning problem? Why not give planning problem and some examples about how to solve the planning problem, and then maybe that will help the LLM improve its performance. It's a very reasonable thing to do, and lots of people have actually used chain of thought prompting in multiple areas. And so the question is basically, it's clear that in COT you're giving extra task problem specific knowledge about a problem and how to solve the actual solution for it. And then the real question is, how much is the system able to generalize from that example? So normally with the humans, we give an example. So I will give you a simple problem, which is not even actually planning problem. What many of you probably heard of, last letter concatenation. What is last letter concatenation? If you have K words, I want you to take the last letter of each of the words and make it a string. That's it. So if I give you dog and cat, you need to give me back G and T. So that's the answer. The moment I told you this, now if I say here is 100 words, can you solve the last letter concatenation problem? 100 words, you will do it. You may complain saying, why are you wasting my time? But you will do it. It's just a mechanically, applying the algorithm. What happens, unfortunately, that's basically the idea of generalization. That's one type of generalization called length generalization. So we asked whether, in fact, LLMs are able to use the advice in this kind of a format. So actually, we did experiments looking at giving advice at different levels of specificity, even in block solved problems. Advice that works for all block solved problems, advice that only works for a certain subset of block solved problems, and advice that works for very specific kind of goals. So it becomes how much are you spoon feeding to the LLM? And we looked at this, and in general, again, before going here, let me just say that part of the reason for my skepticism as to chain of thought's effectiveness is, this guy is called John McCarthy. John McCarthy actually gave the name artificial intelligence to artificial intelligence, the field. And what he basically said is the main goal of artificial intelligence is, in his view, an advice taker system, which can take advice and actually follow it correctly. And that's a pretty darn hard problem to begin with. And so I was kind of skeptical whether they can do it. And so we actually did work, which has been published in NeurIPS 2023, NeurIPS in 2024, and as well as on the chain of thought prompting, as well as React, which is a variation of chain of thought prompting. There's a TMLR paper on that, basically showing that while they seem to help. So for example, if you give last letter concatenation, just look at the last bottom right picture. So last letter concatenation, once you give the examples, of let's say 3 to 4 word last letter concatenation solutions, its performance on 3 to 4 word last letter concatenation increases. That's not surprising. The question is, as I said, you guys will also be able to solve 10, 15, 20, 100 word last letter concatenation problems. Most people, the original COT never really looked at the longer lengths. And so we actually looked at the longer lengths, and we find that even for last letter concatenation, performance just basically craters as the number of words increase. And so much for chain of thought sort of generalizing, the advice from the chain of thought being generalized by the underlying LLM. And this same thing happens in, for example, planning problems, which are the top 3 plots. And we looked at GPT-4 Turbo, Plot 3 Opus, GPT-4. Again, as I said, these are all standard LLMs pre-O1. And we will talk about what happens in O1. I promise you, this is not just the old part. Okay, so that's something to keep in mind, that chain of thought, React, and even fine-tuning, etc., don't necessarily help that much because they don't generalize enough. So in fact, one of the issues with the fine-tuning essentially is oftentimes what people do is they will take a large number of block solved problems and their solutions and fine tune the underlying LLM and then show that it seems to do better on the block solved planning performance. But the question is, if it's not generalizing enough, if it's mostly within the, like if you gave it solutions for 3-4 blocks world problems, and it's only doing well in 3-4-5 blocks world problems and not larger number of blocks, that basically means it's not generalizing. So one of the issues about fine tuning that you have to keep in mind, and again, there was this other slide that I will throw into the Slack after the talk, if I remember. Basically, it's like you have to consider the possibility that you, instead of just solving it with a classical planner, you made the classical planner solve a gazillion problems and then gave all the solutions to LLM to fine tune it. And it's okay to do it if it actually generalizes significantly from the examples that's been given, but there is very little evidence yet, that systematic evidence yet that happens. So that's where LLMs thing is, the chain of thought, as well as, fine tuning, as well as React. As I said, there is another paper on that I won't have time here right now. And then, so anyway, so I can't resist this joke that there's a joke about capitalism that says, not joke actually, I guess it says, a proverb about capitalism saying, give a man a fish, feed him for a day, teach a man how to fish, feed him for life. And the LLM version of that is give an LLM fish and feed it for a day, teach it how to fish 2 fish and feed it for 2 days, teach it how to fish 3 fish and feed it for 3 days, and so on. At some point of time, you get sick of it. This is obviously a caricature, but the point essentially is that they don't learn the algorithm from the advice you are giving. They essentially are, incrementally sort of or fitting themselves to longer and longer unrolling of the algorithm. This is something, this overfitting to longer and longer unrollings of the algorithm is something that we see again in the reasoning models. Just to give you this thing that we'll talk about either in a bit now or tomorrow. Okay, that's where we are. So now, of course, the question is, before we did this in 23, 24, there were tons of papers. Even now, there were several papers already written, both in parallel with us as well as before us, saying they can do planning. The question, of course, is why are they saying LLMs can do planning, and we are saying LLMs can't do planning? It's a reasonable thing to understand how perspectives differ, right? So as a planning person, I can tell you that planning as used in common parlance involves 2 things: planning knowledge, which is what are the actions, what are the preconditions, what are the effects, general recipes, such as how would you reduce a hard goal into a smaller sub goals, etc. And also case libraries, old plans that you have solved and you stored away. This is planning knowledge. And then there's a separate part called interaction analysis and resolution, which is if you can pick pieces, either the actions or sub-plans from the memory, how do you make sure that if one subplan is making goal 1 true, another subplan is making goal 2 true, if you put them together, you are hoping that both goal 1 and goal 2 will become true. But oftentimes in planning, that doesn't happen. That's because of the interaction between the sub-goals. Okay. Now, interestingly, what happens is LLMs are actually pretty good at planning knowledge. For any arbitrary domain, you can actually ask them, what do you think are the actions? What do you think are the potential preconditions, effects, etc.? And they're pretty reasonable in giving that knowledge because they've just been trained on the entire web. But they are bad at interaction resolution. On the other hand, the classical, the traditional planning, even reinforcement learning techniques essentially tend to deal with assume that the model is given, the planning especially model is given by the designer, and they focus on the interaction resolution. And if in fact LLMs if they do well in domains with interactions, in any domain, it would most likely be because subplans can be concatenated and they will work anyway. There's not that much of an interaction between subgoals that is happening. Now, that looks like something that I just made up. Can I prove it or at least show some empirical evidence for this? And here is some empirical evidence. Again, actually, that's from the 2023 paper that I showed earlier on. What we do essentially is we take blocks world, right? And we take the blocks world, and in any planning domain, you have actions have preconditions and have effects. The effects typically are called add versus delete. Add means something is made true. Delete means something that is true is made false. So polarity changes. Okay. So one idea, the reason actually actions start getting into each other's ways is some action is adding a condition that is needed by another action or the goals, and a different action comes and deletes that condition. That's how plans actually go wrong, right? So the question, and similarly, if you put an action, they have preconditions, you need to work on those preconditions. That's another reason why plans become harder to do. So what we did was we took blocks world and made relaxed versions of the blocks world. Relaxation one would be remove all the deletes so that only positive effects are there. And the second is remove all the preconditions. And that basically means any action just will give its effects without asking questions. And you see that if you start from non-relaxed, which is on the right-hand side, to the most relaxed, which is both delete and precondition relaxation together, the green part, which is the number of plans that the LLMs guess correctly, increases as the domain becomes more and more relaxed. So my argument to you is that most of the time LLMs seem to be generating plans. They're not doing what would be called interaction resolution, which is the reasoning part. Really, they are doing some kind of an approximate retrieval, which involves, taking subplans for potentially, subsets of goals and, putting them together. And that oftentimes, if there are no interactions in the domain to begin with, those will already work. Okay, so a sort of a cynical way of saying it is, those are the domains where planning is actually not even needed, and LLMs actually do well in those kinds of domains to some extent. And not surprisingly, if you look at something like Tau Bench, which is an agentic system benchmark, which actually requires like actions and doing multiple actions to achieve goals, it turns out that Tau Bench goes out of its way to remove any actions that wind up getting into each other's ways. That means they actually remove all the interactions beforehand. So mostly the agentic system is focusing on calling the outside services rather than making sure that the calls are properly sequenced, because pretty much any sequencing will work if there are no interactions between the actions. Okay, so here's basically, by the way, I'm kind of, reasonably active on Twitter. Rao2z is my Twitter handle. And so I spend a lot of time doing this sort of stuff. And one of the things that I suggest, I basically was saying, is if you want to argue LLMs can plan, you should pick a domain, basically where there are no interactions between the actions, but then the domain itself might be very open. That means a large number of actions, and potentially nobody even knows what are all the effects and preconditions of all these actions. And so that LLMs seem to be doing well, if in fact there's no interactions between the actions. Whereas if you want to argue that they cannot plan, pick domains where there are actually few enumerated actions, but the action interactions are actually non-trivial. Because at that time, reasoning about which one's supposed to come before what, etc., becomes important, and they seem to do badly. Okay, so actually we're doing well in terms of time. So what I'm going to do now is switch gears and realize that, first of all, standard LLMs were like so yesterday, right? Because basically they're only autoregressive LLMs, and you all heard about these reasoning models. And, not surprisingly, they do better even on the benchmarks that we are looking at. I'll tell you the results in a bit. But what I want to understand is bring the same perspective to the reasoning models and take a look at what are they doing, how are they doing in planning problems. And so the way I would think about reasoning models really is basically standard LLMs plus two parts, test time scaling and post-training. And I will talk about both of them one after the other. And the way to actually understand this, I would argue, a bigger way to understand this is that I would say that the standard LLMs looked at our declarative knowledge mostly. It's the stuff that we have on the web, and that basically recipes, etc. They just can repeat the recipe back to you, or repeat pieces of the recipe back to you. One of the other parts of knowledge that we do have on the web, because humanity has it, so it's on the web too, is procedures, algorithms. And one of the interesting things in an algorithm would be such that if you give it a plan, it can check if the plan is correct or not. And it doesn't care about how long or short the plan is. It algorithmically goes through the plan and checks if it's correct or wrong. And one thing I would argue is that standard LLMs didn't quite know how to use algorithms like the verification algorithms. And test time scaling really can be best understood in terms of these algorithms acting as external verifiers for LLMs being generators. So the LLMs generate verifier tests to see if it is good or bad. And if you have a generate test, you can always improve performance if, in fact, the tester, as long as the tester is actually sound and complete and the generator is reasonable, in the sense it doesn't generate too many completely irrelevant solutions. So that's what we are going to keep in mind. So most of what we have been doing in the last year or so has been looking at, what changes in terms of the planning and reasoning capabilities in terms of the reasoning models. Again, I'm putting the slides thing. Any of you came way too late. Okay. So this picture comes back again. And this picture, basically, we originally sort of said, I was saying that LLMs are probably should be seen, at least I see them as big external system ones for the humanity at large. So the question, of course, is how do you make a system one show system two abilities? That's basically what we're saying. How do you go from system one LLMs to sort of system 1+2 LRMs, are the large reasoning models? That is some terminology that people started using. Okay, so the simplest is, of course, to start with LLM as idea generators. And this is actually one of the biggest uses for humans in the loop. Oftentimes they generate ideas. Humans who are have reasonable expertise can tell whether or not those ideas are making sense. And so instead of generating, you just check whether it makes sense to you. And so that would be a very useful thing from the, in terms of improving your productivity. In fact, one of Linus Pauling's statements is that he got like 2 Nobel Prizes, and somebody asked, how do you get 2 Nobel Prizes? Most people don't even get 1 Nobel Prize. And he said, I get many ideas and I throw away the bad ones. And if you can generate many, many ideas and you're able to throw away the bad ones, that sort of means that you are making progress. And to some extent, LLMs as muses is the best thing that they can do, is the best use in terms of these reasoning scenarios. And the first idea there essentially is that's been called a test time scaling. Now, the test time scaling, essentially, the simplest version of it is, basically something like if you give a solution, if you give a problem, especially if it is a multiple choice question, you ask the LLM 15 times, what is it, A or B or C or D or E, and you take the majority vote. That's like a reasonable thing. It's only probabilistically, people have shown that it probabilistically seems to do better in certain scenarios. Although there are all sorts of issues about this. In fact, I think there's also work that showed that if LLMs do well, even if you actually don't show the question and only show the answers, they still seem to have the same kind of an accuracy. That was one of these papers showing that that's the level at which the data contamination can occur. But one version of test time scaling that I'm particularly fond of, and I'll talk to you more about, is this having verifier in the loop. And it's for 3 different reasons. One, of course, is first I'll talk to you about our own work and what we call LLM modulo, where LLMs are used as a generator and a bank of critiques, either externally, symbolic critiques or learned critiques, or even some cases, LLMs themselves will actually critique the solution candidate that LLM generates and then give a feedback. The feedback can be binary, saying try again, or rich feedback saying try again, these are following things are wrong. Okay, and so I'll first talk to you about LLM modulo, which is this architecture that we've been working with. There's a paper in ICML and a bunch of other papers after that about essentially how to do this in a systematic way with the verifier in the loop with the LLMs. And this is LLM modulo, the verifier. And the other 2 reasons why this is interesting is, I would argue that actually understanding reasoning models is taking what is working in the test time, which is using the verifier in the generate test fashion, and pushing it into the reasoning, into the training time. That's post-training. And I'll actually explain to you how, if you heard of things like RLVR, reinforcement learning with verified reward, what is the verified reward? It's a verifier saying a particular trajectory is correct, ending in a correct solution or not ending in a correct solution. And you're taking that information and then slowly propagating that using SFT or RL techniques to fine-tune the underlying generator. Okay, and then more recently, as of last 2 weeks, we started hearing about these ideas called self-distillation techniques. Some of you probably are following Twitter and realize this. And it turns out really self-distillation is verifier, which doesn't just say yes, no, but also says yes, no with feedback, saying yes and no, this is not an answer because of the following problems in the current solution. And if you use that also in the training, then it becomes essentially self-distillation systems. So understanding the use and understanding the importance and use of verifiers in reasoning problems in the context of LLMs becomes a very important thing. So let me talk to you about LLM modulo, which is basically, if you're just doing it in the test time scaling, so you have a large language model and it generates like a solution, that solution is essentially looked at by a bank of critiques, bank of verifiers or critiques, and they will all basically say yes, no, in terms of are they happy with the solution from their perspective. The simplest version of this would be just a single verifier, but you can have multiple different kinds of critiques. And if all the critics are happy, the solution is good. You send it out. If not, you basically tell the LLM to generate another candidate. And then these critiques, most of the time, can also say what they found objectionable in the current solution, especially, the external critiques, and even also, learned critiques. And so that can actually be sent as a back prompt to the large language model. So originally there was a problem prompt, there is a solution, and there's a back prompt saying this is why the solution is wrong. And then the LLM comes up with a new, now it has a new conditional distribution because the prompt has changed. So it comes up with a new guess. And the question is, that will again be checked by the verifiers. So this is basically a sophisticated generate test approach. And it's going to be sound as long as the verifiers are actually sound. And it's going to be complete in as much as large language model are able to generate all potential kinds of plausible candidates. It's going to be efficient to the extent large language models are not generating random plausible candidates, but they're generating candidates that have a higher prior probability of potentially passing the verifier checks. So instead of large language model, if you had infinite 20 infinite monkeys sitting at the typewriters, that would be also generate tests, but that wouldn't be anywhere near as effective as LLMs, presumably, because LLMs are actually generating stuff that's more likely to be kind of correct, but they're not guaranteeing it. And then the verifiers will look at them. So the critiques, the kinds of critiques that you can be considering, basically are correctness versus style. First of all, you have to differentiate between, you can criticize the correctness of a solution and the style of the solution. And one of the important things is LLMs cannot directly critique correctness. I'll tell you about some work that we have done that shows basically that there is no reason to believe that LLMs which can't generate correctly will suddenly become better at critiquing the correctness correctly. That oftentimes is because of the wrong use of the computational complexity metaphors to LLMs, because a verification tends to be cheaper computationally than generation, but that doesn't necessarily mean that suddenly LLMs will have higher accuracy if the computational complexity is lower. In case you are wondering about that, honestly, a math Olympiad problem would have a higher computational complexity than the simple problems like, farmer goat sort of things, or that Amazon problem on which, LLMs can fail still, right? So whether they fail or not is more of a memory effect than an effect of complexity of checking the verification. Okay, so LLMs can't directly critique correctness, but they can help in critiquing style. In fact, that's actually for style, they are the best critiques available. We can use it that way. I'll show you some examples. Critiques can be binary, such as try again, and are constructive, saying, pointing out the errors in the candidate, suggesting local repairs, even, for example. And the critiques can come from external sources, such as verifiers and simulators, and can be also learned. And when they are learned, they can be learned using any normal learning technique, ML learning techniques, including having like a recursive LLM modulo loop where the LLM itself suggests a piece of code for the critique, and you check whether the critique is correct or not with a bunch of unit tests, seeing whether or not it's working correctly on some number of plans that you know whether they're correct or wrong. And once you get the code at a high enough confidence, you can throw that as one of the critiques, for example. So there are a variety of ways in which you can generate these critiques or pick them from existing literature. And then basically that is the way you can do the bank of critiques. And we basically show, and not surprisingly, and we have a bunch of results, but I'll show you a couple, that essentially the standard LLMs all do improve performance with this LLM modulo, that is with the verifier in the loop, compared to just guessing the correct solution, guessing a solution and hoping for it to be correct. And of course, the more time you allow it to go back and forth, the higher the accuracy. So these results are all essentially oftentimes with just 15 iterations. That means for 15 times LLM guesses, and the verifiers, says whether it's right or wrong. If it says it's right, you stop right then. If not, you will continue up to 15 iterations before giving up. And remember again that when it gives up without critiques being right, no solution is sent out. That way you will never ever send out a wrong solution. It's just that if in fact you wind up getting a solution that the critics are happy with within the number of iterations, then that is sent out. Okay, so we also did this. There's a longer version after the ICML paper. There's a more of a empirical paper that basically talks about a bunch of domains and a bunch of design decisions in terms of actually doing this test time scaling with respect to LLM modulo. For example, comparing binary feedback versus full feedback, and how effective, how sensitive are they to be the number of iterations, etc., etc. A whole bunch of things that are being checked at. And then basically we also look at multiple benchmarks that are no longer actually from the planning community anymore. They are actually, there's this travel planning benchmark that some folks from Ohio State made, and there's a natural plan benchmark that essentially Google folks made. It turns out actually natural plan is not actually a planning benchmark, it's a scheduling benchmark. For people in planning, they know the difference between planning and scheduling. Let me explain to you what the difference is. Scheduling tends to be essentially allocating resources to a bunch of jobs, and planning tends to actually first pick the jobs you want to do to begin with. And planning tends to have these, once you decide to do an action, it has its preconditions, then you have to then find actions to support that, etc. So normal planning tends to have this cascaded choice. Scheduling tends to have a limited choice. But people normally call planning and scheduling problems. And so natural plan is actually a bunch of scheduling problems corresponding to trip planning, travel planning, and also calendar scheduling. And we basically show there too that essentially, first of all, one of the interesting things is those guys separately, after a bunch of of our papers, they separately also show that standard LLMs actually don't do well even on these scheduling problems. And we basically show that LLM modulo techniques actually improve the performance significantly, because it's not magic. It is essentially verifiers in the loop, and with a good generator and a verifier in the loop, you can get accuracy. One thing I want to mention here is the elephant in the room is, I'm not saying, I could have said the following thing. Well, let the LLM generate some sort of something that will be just thrown to an external solver. Like, for example, there are planners outside, like, planners which can take any input and generate the plan combinatorially. I'm distinguishing between combining LLMs with solvers versus combining LLMs only with verifiers. And as I said, in fact, I like that idea a lot better because, first of all, verifiers are compositional. If you actually have critiques for different kinds of constraints, you can just stack them. And then, whereas every time you have new kinds of constraints, the planning algorithm has to be rewritten. That's one part. The second part, of course, is the verifiers in the loop really actually captures what happened to the reasoning system, or what is happening to the reasoning systems, both in terms of R1 and in terms of the self-distillation. So I prefer verifiers to solvers. And then so think of solver as essentially verifier plus search. Normally, I teach in my intro to AI classes that the way you search for a solution is first you know how to verify the solution in a classical method. And if the solution came and bit you, can you recognize it? Once you know a verifier, you invert it, you will get different kinds of search strategies. Instead of inverting, you're just basically saying, let the LLM generate the candidates. I will just use the verifier to check if the solutions are correct or not. And again, as I said, with the solvers, you're stuck with their expressiveness issues. With the verifiers, you essentially can stack them and add more types of constraints with relative ease. Plus, as I said, they also explain what is happening in terms of reasoning models that I'll get to. The soundness here comes from the soundness of the verifiers, and the completeness comes from the completeness of the generator. So the LLM able to generate all sorts of potential candidates. It's only if it doesn't ever generate a candidate that passes the verifier check, then of course the overall system is incomplete. It will never be unsound because the verifiers will never let a wrong solution, to the extent they are sound. It will never let a wrong solution out. But if nobody ever generated a correct solution and if LLM never generated a correct solution to begin with, then essentially that would be a lack of completeness. And there are ways to improve on the completeness using techniques such as diversifying prompts that we discuss in that paper, that ICML paper, that I don't have too much time, but and also the ICML paper as well as that second LLM modular paper that you might want to look at. Okay. One other thing is I mentioned that, verification can be, is essentially something that can be about style as about correctness. And I kind of said, you can't use LLMs for correctness. You have to use it for style. Correctness, you are not guaranteed that when they say it's correct is actually correct. And this, as I said, the reason people assume that LLMs are actually better at verification than at generation is because they realize that generation is oftentimes computationally more expensive than verification, and they think that somehow LLMs would be doing the easier problems more fast, with more accuracy. There is really no reason to believe that. If there's one of the few things I want you to remember is instinctively distrust any claims that say LLMs are good at some problem because it has lower computational complexity. That's not how they work. It is more about what is there in the memory, how effectively these kinds of problems are represented in the memory. That's part of the reason why you have LLMs doing well on Math Olympiad, but not on some of the simpler problems sometimes, because it all depends on what has actually been, what's quote unquote in the distribution, in the training, in the memory. Okay, so to show this, actually, in ICLAY 2025, we have a paper showing self-verification limitations of LLMs, where we take both constraint satisfaction and the planning problems. Constraint satisfaction corresponds to something like 4-color graph coloring or any scheduling problem. They're all constraint satisfaction problems. And then planning problems are the kinds that we are talking about, and show that if you make the LLM judge the correctness of its own guess and put it in a loop saying it generates a solution and then checks itself whether it's good or not, and then tries to go in a loop, and you're taking the same LLM, you're not actually separately training it to be a better verifier or anything. If you do that, in fact, the LLM's performance goes down because there are situations where LLM wrongly concludes that a correct plan is incorrect and moves over it to stop with an incorrect plan because the verification is actually not sound. And we show that, and in fact, that basically self-critiquing is something that you can't depend on the LLMs. If you have LLMs in the loop as well as external critiques, and external critiques are computationally costly, it's okay to do some number of rounds of LLM critiquing for correctness, as long as there is a verifier that checks whether or not it's correct before it's sent out. That would be okay. And not surprisingly, if you look at what happened in the reasoning models that we'll get to in a minute, I mean, either like most likely tomorrow, more of it tomorrow, you will realize that they're actually mostly dependent on the verifiers being present for the problems. That's the RLVR, verified reward, and the reward comes from external verifiers. Okay, so that's the point, that self-critiquing doesn't necessarily work for LLMs, but they are actually very good at critiquing the style, because honestly, partly the reason they're good at it is because there is no other classical technique that is any good at critiquing the style. Style tends to be a huge number of corner cases, and so basically, because most of the time style tends to be these unexpressed preferences of the humans. So for example, all of these are like satisfying a particular goal, but the question is whether the trajectory that satisfies the goal is also preferred by the humans. So for example, the left-hand side bottom, you ask the robot to give you a pair of scissors. It is giving you a pair of scissors with the pointy end towards you. There is nothing wrong in terms of actually giving the scissors. It did give you the scissors, but most of us probably don't want robots giving sharp objects to us with the sharp end pointing towards us. That's an implicit constraint that you typically never write down. And so that is the kind of thing LLMs are actually good at capturing. And so there's a Combe paper that talks about how you can use the style criticism from LLMs to improve the style of the problems, not the correctness, but the style of the solutions. That's about that. In general, I would like to argue, and I'll continue this argument, tomorrow too, in terms of reasoning models, that having a verifier in the loop, which is not just the current LLM, it is basically either something that you train to be a better verifier, or it is actually a symbolic verifier that exists already, or from outside, or even sometimes, by the way, simulators. If you have a simulator for the domain, that acts as a verifier too. Those simulators are written by humans normally. Okay, so if you have those, that's basically the way LLMs do better on reasoning problems. So in fact, alpha geometry, alpha proof, fun search, alpha evolve, all of them use LLMs as idea generators with basically external sound verifiers. And they spend enormous resources fine-tuning the LLMs to improve the density of good guesses, which is what reasoning models do too. We'll be talking about in a minute. The other thing is, if you think about program synthesis community, where basically programs are being generated, if you want it to be correct by construction, the only way to do it is that the code that is generated is subjected to a Python interpreter, where the Python interpreter checks whether the code passes the unit tests or not. And remember, Python interpreter basically is an external sort of a verifier of a program and its solution with respect to a unit test. And so that's sort of a partial verification. And so this is the loop that oftentimes many of the published stuff on program improvement with LLMs also works. So I think it's actually verifiers in the loop, and learning correct good types of verifiers, if you don't have it, etc., is the right way to get the LLMs to do reasoning. And then at least that works at the test time scaling. Now, the last 15 minutes that I have for today, I want to get you into the post-training, which we'll continue a lot more tomorrow, and post-training and its effects. And then my expectation is that tomorrow, maybe I'll also start with letting you ask questions. I can also stop at this point and then see if there are any questions. But let me just go to this next part about at least bring in the test, post-training, how it comes into this picture, and then see where we go. Again, I'm assuming that I have until I have another 15 minutes. That's what my watch says here. So generate test, sort of the problem with generate test, it works, it improves the reasoning, but it is spending user-facing time, right? Because the verifier keeps saying you're wrong until you become right, and the user is waiting for the correct solution. We basically want to, that could be pain in terms a pain point for the customers, because they may not want to wait. They want the generator to be good to kind of give a solution that's more likely to be correct to begin with. Okay, so here actually I would say that Marvin Minsky, who is another of the people who was in the Dartmouth conference along with McCarthy, he said intelligence is integrating test part of generate test into generate part. That's a way of looking at intelligence. So one way you become more intelligent is you take the test and compile it into the generate part, so that you're likely to generate things that will actually pass the test already. So if you think of that as a metaphor, sort of a high-level advice, then think of LLM modulo, right? The same thing that I was talking to you about. And so one basic idea would be that after an LLM modulo solves a problem correctly, because in fact, the critics are happy, now you have solved one extra problem with its correct solution. And so you have, like, if you do enough of the number of times, you have a large number of problems and their solutions. You can potentially fine-tune the model with these more problems and their solutions. And if you do this before the user asks, you generate a lot more planning problems and solve them, and then look at their correct solutions and fine-tune the model. That is essentially post-tuning, post-training. And in essence, you can argue that what's happening there is you are using the critiques to send the signal about what makes a plan correct that is slowly being compiled into the generator. Okay, so the post-training approaches, of course, rely on synthetic data, are often generated with the help of actually classical verifiers, in the sense that the verifier still has to check if the data is correct. So if you know DeepSeek R1, by the way, from here on, when I say post-training approaches, oftentimes we really are talking about only one frontier model that had the guts to write the full paper about how they train their post-trained models, which is DeepSeek R1. They actually published a paper. Google and OpenAI and Anthropic have post-trained models, but we don't know how they do it. So I can't guess exactly what they're doing. I can tell you what R1 is doing, and I can critique it. That's how science works. You tell what you're doing, I can try to understand what you're doing. That's the usual thing we do, right? So in the case of DeepSeek R1, essentially what they're doing is, they will generate, like if you can see in the second picture in the bottom, given a problem, the base LLM generates like K trajectories for this problem. Each of these trajectories has this thing called the think trace, think begin, think end, followed by the solution part, solution begin, solution end. And then the verifier checks which of these trajectories are correct. Okay, and then that's the verified reward. And then this signal is then propagated into the LLM itself through either SFT post-training, or in the case of DeepSeek R1, GRPO, which is a particular form of essentially doing a policy gradient approach. And what we will tell you, tomorrow is that actually the specific form of GRPO that DeepSeek R1 uses is extremely close to a version of supervised fine-tuning called filtered iterative supervised fine-tuning, basic filtered iterative fine-tuning. And so, in fact, it's not like what people tend to think of as a general RL. It is a very particular, peculiar form of RL. And that actually led to all sorts of interesting cottage industry of trying to improve DeepSeek R1's RL. But be that as it may, which we'll spend enough time tomorrow talking about that. One of the things here basically is the post-training can be thought of essentially as generating synthetic data, checking which parts of the solutions are correct according to the verifier. This is the RLVR. This is the verified reward. And then you do RL, or you do SFT post-training, SFT tuning. Either which way, you are changing the parameters of the LLM such that for the problems of that kind, it's now going to generate different completions than it was generating before. Okay. One of the interesting things compared to very standard post-training is that the LLM actually is prompted to both generate a think part followed by the solution part. And tomorrow, a large part of tomorrow's lecture would be what to make of this think part, because there's a huge mythos that has grown around think part, saying LLMs think, the thinking traces tell us exactly what LLMs are doing. You can look at it and understand Even if you don't know how to check the correctness of the solution, the thinking part might help you trust the solution more. And we will try to understand more about whether that makes sense or not tomorrow. But essentially, RL post-training can actually be seen as an incremental compilation of the verifier signal. And then, so this is, of course, the DeepSeek R1's RL, where you generate K trajectories, a verifier evaluate the trajectories that end in correct solution and reward them. And so RLVR really is a form of internal or training time LLM modulo, essentially. And if your LLM modulo is giving binary feedback, then it's RLVR. If you have LLM modulo give rich feedback, that has come to be known as self-distillation. So, for a different kind of a test time scaling technique, if with full feedback, if you actually take the feedback also as part of the learning, then that becomes what's become more recently as self-distillation. So that sort of combines the picture. I'll go more into details about that tomorrow. Okay. So what I want to do before getting into all that is, well, the first model that actually came out, which did the sort of this post-training, we still don't know for sure exactly what they did. This is the interesting part about, it used to be the case that science meant understanding the secrets of the nature. But now you guys are all trying to understand the secrets of Google and OpenAI and Anthropic. Unless you get a job with them, you don't quite know what the heck they're doing. And that's not really science. It's unfortunate, but so be it. But we will basically, it is true that the first model that was different qualitatively from the standard LLMs was O1, or that called the Strawberry, that came out in September 2024. In August 2024, I gave a talk a keynote at ACL 2024. That's the language NLP conference, the top NLP conference, where I basically showed one of the things that actually, in fact, I forgot to mention, one of the things that shows even more clearly that standard LLMs can't actually guess whether the plans that they're guessing are correct or not, is if you give them problems which don't have solutions. Even in a blocks world, I can generate problems that don't have solutions. That means they are unsolvable given the physics of the domain. They're probably unsolvable, right? And if you give that to LLMs, because standard LLMs are RLHF to death, they somehow try to say, you wanted a solution, we'll give you a solution, and we'll try to argue with you that it's a solution. So I showed this example that actually showed up in New York Times later on when GPT-4o came along, saying if a block C is on top of block A, so C is on top of A, and B is separately on the table, can you tell me how to make a stack of blocks with A on top of B and B on top of C, but without moving C? And if you visualize this, you already see that that's not doable, because without moving C, you can't essentially put A on top of B and B on top of C, okay? Because C is actually on top of A to begin with. Remember that, okay? It's not solvable. And yet, for 19 seconds, Strawberry thinks and gives a solution and argues with me that it's a solution. This is fun stuff. If any of you give unsolvable problems to LLMs, they will still argue with you. Sometimes they realize it's unsolvable. Sometimes they actually don't. And so I showed this in my talk, and Noam Brown, who was actually one of the, I guess, involved with the O1 Strawberry, basically tweeted this and said, Rav said this particular problem can be solved, but O1 actually does solve it correctly. So anyway, we took this, obviously there's a, progress, so it would be interesting to benchmark what the progress is. So back in September 2024, basically barely about a week or 10 days after O1, we wrote a new benchmark evaluation paper, which then finally, the final version actually got published in TMLR about O1's planning and learning and scheduling abilities. This is sort of like a stand-in for abilities of reasoning models in solving planning and reasoning problems. And the good news is the baseline performance is significantly better than the standard LLMs. So for example, if you look at the left-hand side of both those pictures, the dotted ones are all the ones that are hugging the x-axis are the standard LLMs, and the 100% is up on there in the dotted line, orange dotted line, and O1 preview and O1 mini, which were the ones that we could access at that time, essentially were blue and red. Okay, so they're much better when the total plan lengths are small. But as the plan length increases, the performance drastically falls down. Okay, which is sort of reminding you, should sort of remind you of what happened with with last letter concatenation. There too, last letter concatenation improved in performance for the size of the problems that you gave examples, but then it started falling pretty badly as you went further. Okay, so we point this out, and we basically point out that it also is actually much worse compared to correct problems. There is still this asymmetry about unsolvable problems, where in addition to the normal LLMs have the hallucination problems, reasoning models have gaslighting problems. They will actually gaslight you into thinking that the incorrect solution they gave is actually the correct solution, because they won't stop arguing also. So we point that out too. And in general, to understand why that is happening, in terms of why is it that if it understood the algorithm, then it should be possible to do 100-word or 300-word last letter concatenation easily enough. And similarly, if it understood the planning algorithm somehow, it should be able to do it for the longer versus shorter plan lengths with the same level of difficulty, with the same level of accuracy. And again, remember that the computational complexity has nothing to do with how LLMs actually solve problems. So the only way you can actually explain it, one reasonable way you can explain it, is essentially what is happening in DeepSeek R1 sort of case. In the beginning, the base model has a reasonable top 15 accuracy, let's say, top 15 accuracy on a set of problems of, let's say, 3 or 4 size blocks problems. Now, this with top 15 accuracy, what it means is it will generate 15 trajectories. By and large, at least one of them will be correct, according to the real verifier. Now, if the real verifier then it says it's correct, then you can take that will become the signal for the RL that can get compiled into the generator, and the generator will start generating trajectories that are more likely to be correct. So what was high top 15 accuracy can be converted over this compilation into high top 1 accuracy on this set of problems, a top 1 or top 2 accuracy. And when you do that, as a side effect, the slightly larger problems now have better top 15 accuracy, and you can rinse and repeat. You can restart this for the larger version of the problems, and you can generate a better generator. So that's basically the way I would argue that it's a reasonable way of thinking of actually what reasoning systems are doing, reasoning models are doing. They're able to compile larger and larger instances of the correct solutions because they have the verifier in the loop. And you have to consider that as a null hypothesis, because otherwise, you can't just assume that because the benchmark is solved, that should be enough. In general, you could basically, in machine learning, people always talk about in versus outer distribution. And the problem is, for reasoning problems, really, deductive closure is more important. So if I show you one last letter concatenation problem, most humans can then solve 15-word, 20-word, 100-word last letter concatenation problems, because they went from the example to the algorithm directly in their head. And what is not clear right now at all is that LLMs are the current standard LLMs right now. Current reasoning models are able to understand, basically pick the algorithms directly. That's what we are essentially seeing. And really, that the inverse of outer distribution says, if I show you mostly 3-4 blocks problems and you do better in the 3-4 blocks problems, you're good enough. But pretty much everything with more number of blocks or longer solutions will be out of distribution. And that is what I would say understanding reasoning is about too. And so you need to think about that aspect. We also showed at that time, of course, September is when the O1 came, then DeepSeek R1 came, and DeepSeek R1 was actually competitive, even at the time we were checking it, and also, of course, it's a public model. One of the things that happened after this is much later, back in April, some folks in Apple basically did the same kind of an analysis, except now that it's Apple, basically it got a lot more traction and people were basically talking about the fact that, yes, in fact, reasoning models have these limitations. And of course, as I was saying, we actually did this before Apple. I think they probably didn't know it. But, since I have friends at New York Times, I made sure that when they wrote an article about this, they cited us in New York Times. Not yet papers, but at least in the newspaper we got cited. Okay, so one last thing today before I stop is, remember we have LLM modulo, right? Now, with all this post-training, LLMs are becoming what I would call LRMs, which is large reasoning models, which have higher accuracy than LLMs. But they're not guaranteed. That was the whole point, because their accuracy is not 100%. What that means is, if you put, instead of LLMs, you put LRMs as the generator, and then you put the verifier in the LLM modulo, instead of LLM, you put the LRM, and you have the same external verifiers. You can improve the LRM's accuracy. And in fact, in the TMLR paper, basically by doing this, you're doing both post-training and test time scaling. That means when users are not there, you spent a lot of time doing post-training, doing synthetic data-based problem solving, and then compiling it into the generator. And then when the user comes along and then gives a new problem, you do this in a more of an LRM modulo way until the solution is actually correct. And hopefully, to the extent LRM is better than LLM in terms of generation, you'll take fewer iterations. And in fact, in the TMLR paper, we show that you can actually improve O1's accuracy with guarantees if you throw it in this, again, another verifier loop, which is very much consistent with what I was saying about starting with the top 15 accuracy on certain problems and then extending it to even larger problems by doing more training on them. In general, I would actually argue that LLMs and LRMs are the amazing 21st century refresh of expert systems. We're all supposed to cringe when we hear the word expert systems, but really, expert systems were experts writing whatever they knew to reasoning systems. LLMs don't need anybody to write because we have already written whatever we have on the web, and they are essentially going from there to do some reasonable type of, kind of problem, type of prompt completion. And unlike standard LLMs, which only could deal with declaratively written, natural language written assertions, I would argue that LRMs are also able to deal with our algorithms, except the algorithms are slowly compiling into the generator, which is a kind of inefficient way. So that's basically where we are. And in terms of even LRMs, if you're deploying them in the agentic systems, you should be careful about their accuracy, because the accuracy is not guaranteed unless you have this sort of LRM modulo kind of an approach. And to summarize for today, what I basically have said is LLMs trained on just web corpora are known to have severe limitations on planning and reasoning tasks. They could, however, be arbiters of style, good arbiters of style. And LLMs can, however, be used as generators in a generate test cycle to give robust planning performance. But this LLM modulo is a form of test time scaling. That's what I was telling you all this while. The improved reasoning abilities can be compiled into the base generator LLM with either SFT or RL. I will go more into what this SFT and RL, how they are completely similar to each other in tomorrow's lecture. And also I will talk about the reasoning traces also then. But the resulting LRMs still have no guarantees, correctness guarantees, but are much better generators. And the post-training is essentially incrementally compiling verifier signal into the LLM. And the last part actually that I'm showing you here, I only hinted here, but tomorrow I'll spend a whole bunch of time. These intermediate tokens that these models spit out, and in fact, it's interestingly, R1 doesn't even spit out, only R1 spits out the intermediate tokens. The frontier models like O1, etc., don't show them anymore. They only show the commentary part. And these intermediate tokens, people have started saying that they have some interesting semantic properties, and that is still questionable. I will talk about that tomorrow. That's basically all I have for now. If there are questions right now, if you have time for questions, I'll take it. Otherwise, please throw questions onto the Slack. I would spend time answering them. And then tomorrow also we'll start with some time for questions and then go into the second part. Thank you again for your attention. I actually can see you on my other monitor, and I know I've seen a reasonable number of people are there. So thank you for your attention. That's the whole reason to do this. It will be much more fun to do it in the midst of you, but so be it. So hopefully you got something out of it. Thank you.
Yeah, thanks so much, Rob. I think we can do a short round of questions. Can you hear the microphone well?
Whatever you are saying, I can hear completely.
Okay,
I saw the
perfect.
clapping being done, but I couldn't hear them, just to tell you. But so that means I can't hear the hall, but I can hear you.
Okay, so I'll just pass the microphone around. Does anyone have questions? Please.
Hi, Subra. Thank you for the lecture. It's Doug Everdeen here.
Hey,
nice
Doug.
to see you.
Hey, Doug.
2006. Fascinating talk. It paints a slightly pessimistic picture of planning in LLMs.
No, it's not pessimistic. It's just skeptical. I mean, I think they're amazing still because we don't have this technology before. When 2006, we had no technology like this. The question is, the way I think about it is LLMs are amazing as they are, and we don't have to add stuff that they don't actually do to make them more amazing. And that's basically the way I would say. I think it's still quite interesting picture. Go ahead.
So my question is, if you were to sort of compare compute for compute, if you were to throw the same number of operations as LLMs use into a classical planning algorithm, would they be outperforming LLMs today?
No, first of all, making that kind of a comparison is actually extremely hard because LLMs have been trained on this humongous amount of data. There is, in a weird way, the way to probably compare it would be take a specific empty transformer, train it on particular types of problems, and then compare it. And in fact, something like that I'll talk to you tomorrow, where we will talk about our experiments with taking a large empty transformer with like 500 million parameter, large by academic standards, and then training them with A-star search traces and to solve the A-star search problems. And then you can compare them to the A-star search performance. There it would be essentially the cost you're spending, of course, is the training cost. And then, of course, you're comparing the accuracy. I don't know if I caught the sense of your question or not.
Yeah, thanks. I think you partially answered my other question about what happens if you use an LLM to write code to create a solver for a particular domain.
So you're saying if you make the LLM to generate code that solves the problem, right? Is that what you're saying?
Yes.
Yeah. No, that is possible. In fact, there's been work of that kind too. We haven't separately evaluated that. We have actually had some work on having in that an LLM modular paper, we had LLMs generate verifiers for particular class of constraints, and that will become the code which make sure that the code is correct because in a recursive LLM modular loop, and then use that to actually kind of basically have that extra kind of a critique on top of LLM. There's also some other work recently. I saw somebody basically, for example, having LLM generate some piece of code that will just work as a heuristic that will help planners, for example. There hasn't been much of a work in terms of, for an arbitrary planning domain, come up with a piece of code that somehow works better than the planners. And I haven't seen anybody do that. It's probably worth checking, but that's probably the place where I would actually expect that the computational complexity will come to bear. So imagine you actually generated an algorithm for Bloxworld, a domain-specific algorithm for Bloxworld. There are theorems showing that Bloxworld is NP-hard, which basically means there is no piece of code that even an LLM can generate that will actually always generate, especially optimal plans in polynomial time, right? But it's still worthwhile to generate pieces of code. That is like a very nice thing to do. That is something LLMs are very much able to do. One of the slides that I forgot to mention is the good thing about LLMs really is you can ask them to generate either the plan, and in fact, I forgot to show that too. We actually did work to, instead of planning, instead of just guessing the plan, we can ask it to guess the domain model. We have a paper in NeurIPS 2023, along with this other paper, where we use the LLM to actually come up with the PDL model, which normally humans write, but LLM can actually guess you a model, and then you can put it in either kind of an LLM modulo loop or LLM modulo with humans in the loop to get a correct model faster. And then that model can then be used by anybody who needs models, including verifiers. So the thing about LLMs is you can ask all sorts of questions. What is the plan? What is the domain? What would the planner's code look like? What is an abstract plan? By the way, that's something that should be very interesting, in the sense, in much of the work in traditional RL as well as planning, abstraction always meant you start at the bottom and try to get to the abstract strategies. LLMs actually can start the opposite way because they have all our abstractions already. So in fact, if you ask an LLM, for example, what do you think would be an abstract strategy for generally solving blocks world problems? If you don't care about the cost, even the old LLMs would basically guess the one which is put all the blocks on the table and then just stack them in the order they are in the goal state. And that is known to be at best twice costlier, twice double the number of steps than the optimal plan, for example. So this is something that's a pretty abstract strategy. To get that for, in a traditional RL, it's be much harder, but for LLMs, basically they know our concrete strategies as well as our abstract strategies, and they can guess both of them. So one of the things I'll remember to do tomorrow is the notion of planning in the era of LLMs is essentially using these additional abilities of LLMs in useful ways. They do everything for you, but none of them with guarantees. Okay, so there's no guarantee for the correctness of the plan. There's no guarantee for the correctness of the domain model. There's no guarantee for the correctness of the abstract strategy. But as you go up this hierarchy, there is no competition. These are the only things that will even do it for you. And so you want to think about how to use it in your planners and the reinforcement learners. I will definitely remember to bring that up tomorrow.
Thank you. Any other questions? Yes. Yeah, thank you for the lecture. You were discussing how using kind of GRPO, you can use problems that have some kind of pass rate in like 15 tries to then improve the pass at one rate, and then you kind of repeat that. I was wondering, how far can you go with this? Like, what are the set of problems that are kind of still unsolvable if you would have pretty much like unlimited resources with increasing difficulty?
Normally, that's a good question. So basically with the incremental compilation, more and more training, you can solve larger and larger problems. But think about the opposite. You need to show that something is unsolvable. Unsolvable problems are co-NP hard typically, or they are in the conjugate of the NP hard sorts of problems. Because to show that something is unsolvable, you should show that there is no plan that will solve it. Why would that be important? If you are, for example, trying to show that your system cannot be broken into by a cyber attack, you need to show that there is no plan of attack that will actually breach the system. And those will require the ability to consider all plans of all lengths and saying essentially that they can't actually, there is no such plan. And my assumption is unsolvable problems would basically be the one that will be a bigger limit for LLMs. Except, of course, sometimes unsolvability can be guessed from, some parts of unsolvability can be guessed from smaller syntactic considerations, for example. But in general, that would be the example that I would have in mind. I don't necessarily have any specific problem that I would bet LLMs can't solve. I'm more interested in understanding what they're doing and what they're solving.
Yeah, thank you. So thank you. Any other questions? Otherwise, I would say thanks again, Rao, and yeah, thanks for the great talk, and see you tomorrow.
Thank you, and feel free to add any questions you have on the Slack if you want me to answer. Thank you, guys. Thank you for your patience.
Thank you.